All right, so we're going to finish up this week by looking at section 5.4. Okay, we're going to split 5.4 into two sections. Okay, and we're going to focus on logarithms. Okay, so we looked at exponentials yesterday, and we're going to see that logarithms kind of go hand in hand with exponentials, kind of like squaring and square rooting. That's kind of the relationship between logs and exponents. All right, so a logarithmic function, it's the inverse of an exponential function. Okay, what that means is it's the opposite. Okay, it undoes it. Okay, so when we have an exponential equation, if we want to undo having a variable in the exponent, we can use a logarithm to solve it. So a logarithm is another function. Right, so if you look on your calculator, okay, we have tons of functions. Right? Squaring is a function, square rooting, sine, cosine, tangent. We haven't talked about those yet, but those are trig functions. And now we're going to look at the two buttons on the left side over by the 7, log and ln. These are both logs, and I'll show you the difference between the two. Right, so there's two kinds of tests we talk about with lines in math. There's the vertical line test, which tells you if something is a function. And then there's the horizontal line test, which it has something to do with a function, but it's also tied in with the inverse. So if you have a picture and it passes the horizontal line test, then that means the inverse is a function. If it passes the vertical line test, then that means itself is a function. Right? So an example of something that does not pass the horizontal line test is something like this. Okay, it passes the vertical line test, which means the picture itself is a function, but it doesn't pass the horizontal line test. If you draw a horizontal line, it could hit the graph more than once, which means the inverse of sine, which is what I drew sine. So its inverse is not a function. Right? So when we get to sine, we'll have to talk about that in a little more detail. Okay, but that's just an example of something that fails the horizontal line test. How about exponential functions? Do those pass the horizontal line test? Yeah, graphs that look, like this. Exponentials. Yes. I mean, they get pretty flat, but they're never perfectly flat. So they do pass the horizontal line test. And since an exponential function passes the horizontal line test, that means its inverse is a function. And I just said earlier, what's the inverse of an exponential? A log. So in other words, if you graph a logarithm, it will come out as a function. So any questions on that reasoning? Exponential functions pass the horizontal line test. That means the inverse of an exponential is a function. And what's the inverse of an exponential? A log. So logs are functions. And if you want to think about it visually, if you graph two functions that are inverses of each other, they're mirror images. But not mirror images like we would think with an axis. They're not a mirror image over the x or the y axis. It's a mirror image over the line y equals x. What's the slope of the line y equals x? Yep. 1. And what's the y-intercept? 0. So the line y equals x, it's a diagonal line that cuts right through quadrants 1 and 3. Right, so let me just fix what the calculator couldn't really do. All right, so what you're looking at here is an exponential function in blue. Okay, it starts out very flat and then goes up sharply. And then in red, that's a log function. Right? And what I did is I drew in the line y equals x. And if you were to take the blue one and mirror image it over that line, you would get the red one. Okay. And that's it. So that's basically what it means visually. Any questions on that? All right. So actually, another thing to point out, exponential functions are one of the fastest growing functions. Right? They go up very, very quickly. So what do you think that means about logarithms?
They go slow.
They're one of the slowest growing functions. Okay? They never level off. They just go up extremely slow. Even when you get into like x values that are like in the tens or hundreds of thousands, the y value might only be at like 4 or 5. So they're very, very, very slow growing. Right, so this is a logarithmic equation. Okay, and in order to solve it, you'd have to know a couple of the numbers in there. But the way you pronounce it, you read it left to right. Y equals log base A of x. Right. So if I had something like y equals this, how would you say that?
Y equals log base 2 of 6.
Yeah, y equals log base 2 of 6. And if you're writing it on lined paper, just to kind of show you how it would look, the log 6, that's right on the line. Okay? The base 2 is actually below the line. So the 6 is not an exponent. The 6 is right on the line with everything else. It's the 2 that's actually below the line. If you had an exponent, it would be up there like that. Okay? All right, so we just talked about how to pronounce that. And this part right here, this thing that I just circled, that's called the argument. Okay? All functions have arguments. It's just the thing you plug into it. So for example, if I put this here, the square root of 3x. 3x is the argument to the square root function. It's just the thing that I'm plugging into it. Okay? In this problem, 6 is the argument to the log function. Okay? It's the thing I'm taking the log of. Okay? If the base is 10, that has a special name, and that's called a common log. The common log is one of 2 bases that your calculator can do directly. You have a button for this, and for one other one.
Is that what we learned in algebra 2?
You might have done a little bit with logarithms. I'm not sure. Did everybody do logarithms?
Yeah.
I never did logarithms.
You don't remember? You do?
I do.
You do? Yeah, you might have learned a little bit about it. Anybody not too sure about logs? Maybe first time seeing some of this stuff? Yep. Okay, so since the common log occurs quite a bit, if you ever see something written without a base, you always assume it's the common log. So if I just wrote this problem down, log 12, and I don't put a base, you assume the base is 10. Okay, and on your calculator, the button for the common log, it says log, and it's right next to the 7. Okay, so if you wanted to, you could press log, you could type something in, and get the answer.
What is log equal to?
We're going to talk about
Nothing.
the formula
Okay.
in a second. Like what is log 12? Like how did the calculator get whatever it was that I had?
It's 1.0.
All right, so the second special log, okay, is when there is a base of e.
Isn't E like 2.71?
Yeah, and we talked about the number e yesterday. Okay, it came from that exponential function 1 plus 1 over x in parentheses raised to the x. Right? And I said that horizontal asymptote in that function is going to come up today, and it's coming up right here. Okay, so the other special base, besides having a base of 10, is having a base of e.
Is that the ln one?
Yep.
Where do you find E on the calculator?
I'll show you that in 1 second. It's a second button.
Second division.
All right, so log 10, that's a button you have on the calculator. That's called the common log. And log base e, that's called the natural log. Now, a lot of times you won't ever see this written, log base e, okay, because it's used quite a bit. They come up with a shortcut for writing it, and they use this shortcut on the calculator as well, and it's ln. All right, so if they asked you to find something like the ln of 8, okay, what they're asking you to do is find the natural log of 8. Okay? Or you could also say the log base e of 8. Okay, so ln and log base e mean the exact same thing. ln is just an abbreviation. But it's important to remember that that abbreviation hides the base. You've got to remember that if you write ln, you're talking about a log with a base of e. Okay, and that'll come up a couple places today. Okay, and just in case I didn't show you where that one is, the natural log button, it's right below the regular log. And that's the natural log of 8. Somebody asked about e, if you're looking for that. It's second division. So any questions on the names of the two special logs? Right. If you have a log with a base other than 10 or e, we just say that that's a log base, whatever the number is, log base 6, log base 12. And you don't have a button on here for typing in logs other than base 10 and base e. So if I wanted you to do a problem like that, log base 2, there is a way to type it in, but not with just one button. Okay, so we'll have to talk more about that probably next time. All right, so the domain and range, if I bring the graph back up, you can take a look at that and see. But I said the domain is 0 to infinity. And if you look at the function in red, it starts, has a vertical asymptote at 0, on the y-axis. So the domain is from 0 to infinity. It doesn't include negatives. You can't take the log of a negative number and get a real answer. Okay, you can do it and get an imaginary, but we're not getting into that today. Okay, so for our purposes, domain 0 to infinity, and you can do you can't do 0. Okay, so it's everything from 0 to infinity, not including 0, and the range is from negative infinity. It goes down forever. And it goes up forever. It goes up extremely slow. Okay, it almost is going to look like a flat line, but it will keep going up very, very slowly. Okay, so that's where the domain and range come from. All right, so next we're going to look at a formula that's going to allow us to change something that's written in exponential form into log form, or vice versa. Okay, so we'll be able to take a problem like this and change it into a problem that has a variable as an exponent. Or I can take a problem that has a variable as an exponent and change it back into something with a log. Okay, so we'll practice converting both ways. Okay, and there's your formula. Okay, and what I tried to do is put boxes around where the things move. Okay, so you just have to keep track of kind of what moves where. All right. So when I'm trying to rewrite something from a log into exponential, the first thing I look at is this number that's written lower. Does anybody remember what I called that when you pronounce it? Log base. That's the base. When you rewrite something from log form into exponential, it's still the base. Okay? It's going to be the base, and something's going to have an exponent. Okay? So the base on your log becomes the base on your exponential. Okay, so if you can remember that, and then if you could also remember that a logarithm always equals the exponent. Right? So a logarithm is an exponent. So when I type in something like I did before, log 12, okay, and I get 1.08. That 1.08, this number right here, that's an exponent to something. Okay? I haven't shown you what yet, but it's an exponent. So anytime you calculate a logarithm, you are finding an exponent. So that's why I always say the logarithm is always equal to an exponent. And if you can remember that, when you write it as an exponential, whatever the logarithm equals, put that as your exponent. All right, so there's really three things you have to put. That's your base, that's your exponent, and if you figure out where two of the three things go, then there's only one place left for the third thing. The argument on the log ends up going by itself on that side. All right, so let's just practice kind of changing a few of those. All right, so there's three things, and when I rewrite it, you have three spots. Okay, let's start with the base. What's the base on my log? 3, and that's going to be the base when I write it as an exponential. Okay, logarithm always equals what kind of number? Exponent. The logarithm is always equal to your exponent. That's my exponent. Okay, what's the only thing I haven't used? X, that's the argument, and that has to go right there. Now, in this particular problem, you can't solve it because you don't know two things. But if you knew y, say y was 2, then we'd have x equals 3 to the 2, and then you could solve it. All right. How about this one? How would you rewrite example B as an exponential expression? Yeah, x equals, my base is 5, and the logarithm equals your exponent. Now, again, you can't solve that because you're missing two things. Okay, I have to give you a little more information. Any questions on that one? All right. So now let's try the other way. Here's something that's an exponential. I want to write it as a log. Well, if I'm going to write it as a logarithm, what do you think the first word I should write down is? Log. Okay, if I'm going to change it to a log, write the word log. Okay, what's going to be the base on my logarithm? 1.2. It's the base from my exponential. Okay, the number that's lower than the exponent. That's my base. And a logarithm always equals what kind of number? The exponent. So the only thing I have left is the argument. What am I plugging into the log function? M. I'm taking the log of m with a base of 1.2. Now, in this kind of problem, this usually wouldn't make sense to do what we just did, because if you were going to solve it, you could just type 1.2 cubed into your calculator. Right? But we are just practicing changing it to log form. Right, so we'll start with the word log. This is log, and what's my base? The base is e. And the logarithm is going to equal what? My exponent, which is b. And the argument to the log function is 9. Now, that can be simplified a little bit. You probably wouldn't see something written like this. Anybody tell me how I can simplify log base e? Yeah, we can change log base e to ln of 9. And this is a problem that you would want to do what we just did. Okay, so if I asked you to solve this equation, the answer is the ln of 9. Okay, so if you wanted, you could just type in ln of 9 and get 2.197. So in other words, if you take e and you raise it to the 2.197, you get 9. Okay, so we just solved for the exponent. What would you raise e to get 9? It's about 2.197. Hey, any questions on that? Okay, but again, don't worry about the decimal here. You don't have to write it. How about C? Log, Angie, what would be my base there?
The base would be A.
Yep, the base is A. And logarithm always equals what kind of number?
Exponent.
Exponent. So how about, Jeff, can you tell me what my exponent would be?
24, not 4.
4, yep, that's what's up higher. And 24, that's my argument that I'm going to put into the log function. I basically gave you 3 different examples. One where the variable was on the right by itself, one where the variable was an exponent, and one where the variable was a base. We just did each possible type. All right, I want to show that log base 2 of 8 equals 3. Now, if you knew how to plug this in on the calculator, you could evaluate this and tell me that it equals 3. But we don't know how to type in a base 2 on the calculator. What are the 2 bases the calculator can do? 10 and e. Okay, so I can't do base 2, so we got to do this a different way. And the only thing we know how to do right now is to change from log form to exponential. So let's just change it and see what happens. Amanda, what's my base here? 2, yeah. 2 is my base, because that was the base on the log. And the logarithm always equals your exponent. So 3 is my exponent. And what's the only thing I haven't used? 8. So let me just kind of draw arrows. That's your 2. That's your 3. And that's your 8. Now, is that true? Does 2 cubed equal 8? Yeah. So we showed that log base 2 of 8 is equal to 3. All right, let's try this one. Now, when you see a problem like this, it could be written like that in the homework. It could just say evaluate. So you're like, well, where's the thing on the other side? You can put something there. This is equal to question mark or x. It's equal to something. So if you want to put something on the other side, you can. All right, what's my base here? Trevor? 5. And my exponent? X, logarithm equals my exponent. And Ayla, what haven't I used? 1/25. Now, if you get stuck here, pretend that it was this. Instead of 1/25, pretend it was just 25. 5 to what power is 25? 2. Now, we don't want to have 25, we want 1/25. So what kind of numbers do you need for exponents that cause things to flip? Negatives. So this would be not 2, but -2. Okay. Now, if 25 wasn't a power of 5, you couldn't do this. Say I made this 1/24. You can do it with a calculator if you know how to type in a base 5. But you wouldn't be able to do what we just did. All right, so this one, they want us to solve the equation. And this time, the variable is the argument. So any suggestions what I should do with that to try to solve it? Yeah, that's the only thing we know how to do right now. Change it from a log to an exponential. Okay. And can anybody tell me the whole thing? You don't have to tell me the answer, just the equation to get the answer.
Is it 5 to the 1.5 power equals x?
Exactly. Just type that in on your calculator, and that's the answer. In fact, I'm not even going to do it. But it's 5 to the 1.5. All right. How about this one? It's going to be a little different when you solve it, because the first one had the variable as the argument. This has the variable in the base. But I still think you'll know how to solve it. Yeah?
Is it x to the second equals
Yeah. X is my base. 2 is my exponent. 3 goes on the other side. And now how do I solve that?
you would square
Square root both sides. And I get x equals whatever the square root of 3 is. Now, when you take the square root, how many answers are there? 2. But when we talked about logarithms, whether you're talking about the base or the argument, what did I say the domain was? It always has to be what kind of number? Positive. So you can't use the negative answer. Okay, so the answer is just the positive square root of 3, the principal root. Okay, so never any negatives for the base, never any negatives for the argument. All right, so now we're going to look at some special patterns, okay, that can come up with logarithms. And these are just patterns to recognize. There's not really a lot of algebra to do here. It's just kind of something special. If you have something in this pattern, a raised to the log base a of x. Okay, let me see if I have one with numbers I can show you. It's just like example 6a. 2 to the log base 2 of pi. What ends up happening if you want to simplify this, okay, pretty much everything cancels out because the bases match. That's the key. The base on the log matches the base here. And the answer that you get is whatever is sitting right there. Right, so if I were to simplify this one, the bases match. Okay, so the answer that I get is whatever is sitting right there. So what would all that simplify to? What is it? Just pi. Okay, any question on why that one simplifies to pi? It's just a special pattern. If you change one of these 2's to like a 3, then it doesn't work. Right? It's just when you have a 2 and then a power, and you have a logarithm in the power, it cancels out. Okay, example or rule 2, that's similar to this one. You still have something matching, but it's not quite the same pattern. It says log base a of a to the x. The first a is your base, and then the a to the x is your argument. Well, as long as these two numbers match, okay, what ends up happening is everything there cancels out, and the answer that you get is whatever the exponent is on the argument. So if you were to simplify example 6b, what would you get? -4. Okay, there's really not any work to do. It's just you're looking for a pattern. Okay, let me show you. I'm not going to do this for rule 1. I could, but let me show you why rule 2 works. Okay. There's your base. There's your argument. And there's the thing that's on the other side. Okay, so let's change this from the form it's in. What form is rule 2? Is that a log or is that an exponential? Yeah, it's a log. Okay, overall, it's a log. It has an exponential expression in the argument, but the big picture here, it's a log. Okay, what's the base on this log? A. Now, logarithm always equals what kind of number? Logarithm always equals my exponent. So what's my exponent in number 2? X. Okay, so I'm writing everything in the color that I circled it where it's moving. So I used the a, I used the x. What's the only thing that's left for the other side? A to the x. Okay, so by rewriting rule 2 in exponential form, a is your base, x is your exponent, and the argument goes by itself on the other side. All that rule 2 is saying is something equals itself. Of course that's true. That's the reflexive property. You might not have recognized it because it was written in log form, but certainly if you rewrite it without the log, there's your reflexive property. Something equals itself. Okay, this is going to be another property we will explain why this one's true. It says log base a of a equals 1. Right, so an example of that would be if I said, what is log base 4 of 4? 1. All right, so let me circle some things. Base, argument, thing on the other side. Okay, let's change that into log form, exponential. Okay, what is my base? Yep, the one in blue. That's my base. Logarithm always equals what kind of number? Exponent. So 1 is my exponent. And what's left to go on the other side? Yeah, the a I circled in red. This is saying that if you raise anything to the first power, it doesn't change. Anything to the first power is itself. And very, very basic rule, just now written as a log. So you might not have recognized it. Does anybody know what the fourth log rule is saying? Log base a of 1 equals 0. So you could have log base 6 of 1. It would come out to 0. Log base 10 of 1 comes out to 0. Right. Anything to the power of 0 is 1. Here's your base. There's your argument. There's what's on the other side. So write your base. Your exponent is 0. And the argument goes by itself on the other side. So anything to the 0 power is 1. Again, another very, very basic algebra rule, just written as a log. Okay, but these rules really are nothing new to you. They're just written a little different. All right, so I didn't have an example for rules 3 and 4, but an example for rule 4 would be if I said, tell me what the log base 6 of 1 is. Yeah. The answer there is 0. Okay. How about example C? Does anybody see what rule that one is? It's hidden a little bit, but it is one of those 4 rules. Yeah, Allie?
Is it rule number 2?
Yep. Can you explain how you could make that look more like rule 2?
Well, concerning its ln, it means log to base e.
Yeah, you can change ln to log base e. So what I circled in red, I just wrote out the long way. Now copy the rest of the problem. So you have a log where the base on the log and the base on the argument match. So what would be the answer of the ln of e to the kt? Yeah, kt, whatever k times t is. We don't know what that is, but that's what it would be. Okay, so just some basic properties that if you come across some expressions like these in the homework, gives you some tricks to simplify them. Okay, especially rules 3 and 4. I don't see rules 1 and 2 as much, but 3 and 4, they come up quite a bit. All right, so the last thing we're going to look at is properties we can use to take logarithms that are separate and combine them, or you can take logarithms that are already combined and separate them. You can do it either way. Okay, some of these properties I'll show you why they work on the calculator. The last property I'll actually kind of prove to you with algebra, but we're not going to prove every one of these properties. Okay, so the first rule with logarithms, it's for the logarithm of a product. And this rule can be extended to as many factors as you have. I'm just doing it for 2, m times n. But if you have a logarithm of a product, that can be separated into the log of a sum. When you separate it, the base always stays the same. Base A, base A, base A. The product gets replaced with a sum, and the argument to your first log is your first factor. The argument to the second log is your second factor. Okay, so if you want an example with numbers, you could do something like that. Now, I'll show you that this works. And the easiest way for me to show it on the calculator is to use a certain base. I have 2 bases I could pick from to show you this rule. Yeah, I could use base 10. And I could type log of 4 times 5. Or I can type it as log 4 plus log 5. I get the same thing. Now, what is 4 times 5? 20. So can anybody think of a different way that I could have split up the number 20? I could have done 10 and 2, and that will also give me the same answer. Any 2 numbers that multiply to give you 20, if you type it into this formula, would work. You could do 40 and 1/2. You could do 100 and 1/5. You could do anything. Any numbers that multiply to give you 20. Okay, so that's a rule for splitting up the log of a product. Okay, we also have a rule for splitting up the log of a quotient. Anyone have a guess how a quotient is going to split? Product splits as a sum, and it's pretty much what you would think. Yep. The only thing you've got to be careful is with subtraction, it is not commutative. So you have to do log of the top minus log of the bottom. Base stays the same all the way through. And the nice thing about these formulas is they work with any base you want. I mean, I only showed it to you on the calculator for base 10, but I could have done the ln. That would be easy to show you on the calculator. Ln of 20 equals the ln of 4 plus the ln of 5. Or if I know how to type other bases in on the calculator, I could show it to you for any base you want me to show you. Okay. So here's same type of example with numbers. Log base A of 4/5 equals log base A 4 minus log base A of 5. Okay, and the last rule we're going to look at for combining and splitting logs has to do when you have an exponent on a log. All right, so before I show you the formula, I'm going to show you an example. So leave a little bit of space to write the third rule, about the same amount of space as you did for each rule. Okay, and let's look at this. Log, the base doesn't matter, so let's just do base 10. So log base 10 of x cubed. Now, say I don't understand what it means to cube something. How can you write this out? Yeah, you could write log of x times x times x. Now, if you look at that, does that look like any one of the rules that I've gone over so far? Yeah, it's the logarithm of a product. It's extended to 3 factors, but I told you you could have as many as you want. So if you have a product splits apart as what? Addition. When you have 2 factors, it splits into 2 things. How about if I have 3 factors? It's going to split into 3 things. Log plus another log plus another log. The base is 10 on all of them. That's not changing. And now take your first factor, put it as your first argument, second factor, second argument, and then third factor, third argument. Okay, so what's my argument for the first log? X, second log, and third log. So now if I had a log x plus another log x plus another log x, that's 3 of the log x's. So the shortcut, when you have an exponent on the argument, all you have to do is take the 3 and put it in front. And the reason why I just went through. It's really rule 1. It comes from rule 1, except each factor is repeated. It's the same. Okay, so you have an exponent. Just take and put it in front. So when you're doing the homework or on the test, if you see a problem that says express powers as factors, that's what I did right here. 3 is a factor, log x is a factor. If I leave an answer like this, that's leaving me as a power. Okay, so if it says to write your powers as factors, basically that means move the powers in front. Okay, so now we'll finish up just by looking as many as we have time for how we combine and split logarithms. All right, so let's look at the first one. Log base 4 of 3x. Anybody tell me how that's going to split? As a sum or a difference? Sum. What's going to be the base on each log when I split it? Yep, it's going to be base 4. And Taylor, what's going to be the argument to my first log right here? 3. And Grayson, how about the argument to my second log? X. And that's it. It didn't ask me to simplify anything, and we don't know how to simplify this yet. You can. This is a number if you know how to type in a base 4 log. But we're not doing that. Okay, let's look at example B. Log base 2 of 5 times r cubed. Okay, Pacey, how is this one going to split? As a sum or difference?
As a sum.
Yep. What's going to be the base on each log?
5 and r.
Those are going to, well, part of what you said is going to be my argument. But what about my base? So the 5 is going to be good for here. I'm going to come back to the second thing you said, though.
Would you write it as?
Put something down here.
Log 2.
Yeah, we got to have the base of 2. Okay, whatever the base is on the original, that's the base on the split up problem. Yep, so that's good. And I like that he said 5 is my first argument. Now I think you said r was the second argument.
Wouldn't it be 3 log base 2?
So yeah, we're going to do that in 2 steps just so people can see it. So what would I start by putting right here? R to the third. But then it says to express powers as factors. So that r to the third, where would the 3 move? Into the front. If you want to do that all in one step like that, that's fine. Okay, so it's log base 2 of 5 plus 3 log base 2 of r. All right. Anyone think they can tell me the whole answer to that one? It's the first one we've done of this type, so if you get stuck, that's okay.
Log base 9x.
Log base 9 of x.
Minus log base 9.
That's the big difference here. Minus log base 9 of 2. Any questions on that? All right. And I told you it works for any base, log, ln, whatever base you want to use. So anyone think they could tell me the whole answer here?
Yeah.
About Kayla, could you start me off?
Log E.
Yep, you could write log base e, or let's use that abbreviation since we have the ln. Yeah.
A minus 3 ln y.
All right. So what? Can you tell me that first term again? ln of.
A.
All right. Just be careful because since 8 is in the bottom, that has to be the second one. If it was addition, it wouldn't matter. You could do it in either order. But with subtraction, you got to put this as your first one. So what would be my argument for the ln?
Y.
Y. What about my exponent?
Go in front.
Yep, the 3 would move in front. And then minus
ln
ln e. Yep. Okay, any questions on that one? All right, so let's look at one like this. Now, here you have to be careful, and something's going to come up that I taught you about radicals. A different way to write a square root symbol. Okay, you don't have to use the symbol, and you'll see why you have to do that in a second. All right. So overall here, this is a fraction. Okay, so what I'm going to do is start just by splitting the fraction up. Log base a of the top minus log base a of the bottom. Okay, that's the first step. Now I want to look at this first one. Does anybody remember a different way you can write a square root without using the square root symbol? And that's going to be important because it's going to allow us to use one of the rules I just taught you if you do this.
X squared plus 1 to the 1/2.
Yes. And I'm going to come back to that 1/2 in a second. So when they say to express powers as factors, that includes hidden powers as well. Anytime you have a square root, there's a hidden power there of 1/2. Okay? And that's what we learned about radicals. Okay, now minus. Now, how is the second log going to split? It's something times something. That second one is going to split as a sum. Log base a plus log base a. But remember, when you split this apart, you're subtracting this entire thing. So make sure you leave that distributive property intact. Okay, so anything you split this apart into, they are both subtracted because that's how it was originally. The whole thing was subtracted. What's going to be my first argument? And the number in front? My second argument? X plus 1, there's nothing you can do with that. And then the number in front? 4. And now the only thing I have left, I'm just going to kind of cheat and copy that, or you could just erase something from the last step. Where does that 1/2 need to go? In front. That's the mistake a lot of people make when it says to express powers as factors, they miss the hidden power in the square root. So always change your square root to a 1/2 power. Okay, and that's about as complicated as it can get for splitting logs apart. And that's a good place for the final answer. If you wanted to distribute the negative, you could write minus 3 log base ax minus 4 log base ax plus 1. Or leave it like that. All right, so last thing we'll look at really quick is just taking a couple that are separate and combining them. So it's just the reverse of this. Okay. What would be the first thing you'd have to do here? Focusing, let's start with the second part. If you wanted to recombine it, undo everything in the reverse order. So put the 4 back as an exponent. And now you have the log of a sum. So what would have you had to have originally if something split as a sum? Multiplication. Would have had to have been 7 times 3 to the 4th. And now you could just do that out on your calculator. So that's 3 to the 4th is 81. 81 times 7, I think, is 567. No. So it's log base A of 567. Okay. Just recombining it. Let's look at, I only have one more. So, well, I'll just finish this last one. In that last part, I think I'm going to have to change one number to make that work. Let's make this 71. Okay, so you'd have ln of 8 to the 2/3 minus ln, what's 3 to the 4th? 81. What's 81 minus 71? 10. Now, if you don't know how to do a fractional exponent, you can type it in on the calculator, but what it means is do 8 squared, that's 64, and then take the cube root. The cube root of that would be 4. Again, just use your calculator if you need to. And now if you have subtraction, what would that have been originally? Division. 4 over 10. Or 2/5. Okay, so we can practice some more combining and splitting logs if we need to tomorrow. Okay, so don't forget, I'll be after school today if you need extra help. Homework on 292, okay, 1 to 7, 13 to 17, 21 to 27, and 29 to 33. A lot of very quick kinds of problems. Yeah, it's combining logs, splitting logs, changing logs to exponentials, and vice versa.